Welcome dear students, welcome back to physics class. Okay, till last class from the fourth lesson, moving charges and magnetism, we had discussed the magnetic field due to a very long cylinder, which is the point which is at the inside the cylinder and the point to which the magnetic field determined outside the cylinder, and we have seen the graph also related to it. Okay, now we are going to discuss about the solenoid and toroid. So we know the many electrical gadgets that uses some equipment to produce a magnetic field. That is nothing but a solenoid. Already we have discussed this in our 10th standard. So in solenoid is nothing but a long copper coil which was wounded on in non-insulating frame. Then the terminals are connected to the battery. Okay, then the ends are connected to the terminal of battery. When a current passes to the wire copper coil in the form of a turns, in the form of a long helical shape, then each circular turns that produce the magnetic field with respect to the direction of the current. Then in every turns the magnetic field is added up, then the total magnetic field is determined, and this magnetic field is similar like a bar magnet. So one side it acts as a north pole, another one side it acts as a south pole. So from north pole to south pole, externally the field lines emerge and ends in the south pole. Internally from south pole to north pole, that is the uniform magnetic field. So what we have discussed, what we have studied in our 10th standard, the same we are going to look at very deeper. Okay, so the solenoid and the toroid. First, solenoid. What is a solenoid? It is a piece of, it is an instrument or equipment. It is an equipment used to produce magnetic field. A solenoid is an equipment used to produce magnetic field. How it looks? On a non-insulating frame, this is a non-insulating cylindrical frame. Over this non-insulating cylindrical frame, a copper coil is wounded. So a copper coil is wounded. Then the terminals are connected to the battery with a key. So the positive terminal of the battery, from which the current entering through the coil, and current is coming to the negative terminal. So this is the direction of the current. So in every turn which carries a current, with respect to the direction of the current, it produces the magnetic field. So one side is completely act as a south pole, another one side is completely act as a north pole. Why one end is act as a south pole, another one is act as a north pole? That we will discuss in the next lessons. That is earth magnetism. Okay, in that lessons we are going to discuss the magnetic field produced by the bar magnet is similar to that of a solenoid. But now we are going to find the magnetic field produced in the solenoid in generally. அதாவது இந்த ஒரு solenoidல magnetic field எப்படி produce ஆகுதுன்னு பார்க்க போறோம். Okay, so this is a long cylindrical solenoid. This is a long cylindrical solenoid. Here the length of the solenoid is, here the length of solenoid is much greater than the radius of each turn, because it's a circular coil, no? So over circular coil ko radius irukum. So the length of the solenoid is much greater than the radius of each circular loop. Okay, now this cross sectional view of the solenoid, how it looks, we are going to see the cross sectional view. The solenoid அப்படியே வெட்டினா எப்படி இருக்கும்? Cross sectional view of the solenoid. Look at this. In this cross sectional view, so at one point the field is emerging out, in another one point the field is emerging in. So from here the field is emerging out, here the field is entering into it. So all these cases the field is entering into it, the electrical field is entering into it. So listen, the cross sectional view. At all these points, the upper ends, the field is emerging out. At the lower portions, the field is entering into it. So this is the wire. So here the field is emerging out, so we can denote it by dot. Here the field is again into the insulating frame, so it is denoted by cross. Okay, so the direction of the magnetic field can be verified by right thumb rule. So when the field is emerging out, then there is a current is emerging out of the plane, then the field line produced will be anti-clockwise. So here the field line produced is anti-clockwise. So all these spaces, the field line produced is anti-clockwise. So what is the direction? It is anti-clockwise. So this is the direction of the magnetic field produced when it is emerging out of the plane. But here the field is into the plane, so it is in a clockwise. See, so in the lower portions it is into the plane, so we can say it is clockwise. So here it is clockwise. So this is how we will find the direction of the magnetic field. In the upper portions it is in anti-clockwise, in the lower portions it is in a clockwise. So between the solenoids, the field lines emerge externally. The field lines which emerge externally from where to where? Externally from south pole to north pole. Is it so? No. Externally the field lines emerge from north to south poles. So externally from north to south pole. So externally the field lines emerge from north pole to south pole. But internally, inside, the field lines from south to north, which means at the center the magnetic field, which means inside the solenoid the magnetic field is uniform, that is parallel from south pole to north pole. So this diagram that depicts the cross-sectional view of the cross-sectional view of the solenoid. Also we can say we can draw the diagrams like this. So all these places it's a dot. The current is emerging out here into the plane. So the field lines from south to north internally, externally from north to south. Again from north to south externally, and internally from south to north. It is a uniform magnetic field. Okay. So now we are going to find the magnetic field inside the solenoid. So how to determine the magnetic field inside the solenoid with respect to the cross-sectional view itself. Listen. So basically in a motor, like many devices, uses the solenoid like arrangements, either solenoid or toroid. According to the convenience we may have the shape, but both also used to produce a magnetic field. It may be a solenoid or toroid, both is an equipment used to produce a magnetic field. Now we are going to determine the magnetic field produced by a solenoid only. Toroid in the next topic. So in this cross-sectional view, This is the upper end of the solenoid, and this is the lower end of the solenoid. So the upper end, the field is emerging out. So all these places it is dot, it is a dot field. So here all these places it is a dot field, but here we have a cross into the plane. So this is a cross section view of the solenoid. Okay, now the magnetic field inside is uniform, that only we are going to determine. So the magnetic field lines that passes, this is the magnetic field line. This is the direction of the magnetic field line. This is the axis of the solenoid. So this is the axis of the solenoid, and this is the direction of the magnetic field inside the solenoid. Okay, so this is the direction of the magnetic field. Now we are considered the imaginary Amperian loop. The imaginary Amperian loop is a rectangular Amperian loop. Let us take that is PQRS. So this is an imaginary Amperian loop. PQ. This is an imaginary Amperian loop. This is not P. PQRS. So PQRS is an imaginary Amperian loop. Here the arm PQ is along the direction of the magnetic field, but the arm QR is perpendicular to the direction of the magnetic field, and the RS is opposite to the direction of the magnetic field, which is outside. This is outside the solenoid. This is outside the solenoid. And the SP is perpendicular to the direction of the magnetic field. So we are going to calculate the magnetic field inside the solenoid. So let PQRS is, let us take PQRS is an Amperian loop. Amperian loop. Okay. In this Amperian loop, PQ is along the direction of magnetic field. PQ is along the direction of magnetic field, and QR and SP is perpendicular to magnetic field, and RS is opposite to B but outside the solenoid. Okay, these are the conditions we have taken. So here how the magnetic field is produced inside the solenoid only our aim to determine. Moreover, inside the solenoid the magnetic field is uniform and parallel from south to north pole, but externally from north to south pole, but internally the magnetic field is uniform, okay, at every point. So that magnetic field only we are going to determine. Therefore, the total magnetic field in rectangular loop PQRS is determined by, it is a closed loop only, no? So closed integral PQRS and d vector dl, which is equal to line integral of each arm, okay, which is equal to the, what is it, which is equal to the line integral of magnetic field, which is equal to line integral of each arm magnetic field, that is closed integral PQRS b vector dot dl vector, which is equal to integral PQ b vector dot dl vector, and the cos, what is an angle? It is along the direction of the magnetic field. Okay, PQ is along the direction of magnetic field. So cos theta, what is the theta? It is 0 degree plus next line integral QR B vector dl cos 90 degree plus integral RS B vector dl, but which is outside, this case is outside the loop, plus integral SP B vector dl vector into cos 90 degree. Okay, as we know already, cos 0 degree is equal to sin 90, which is equal to 1 now. So this value become 1. So we have, what is it? Integral PQ B vector dot dl vector plus, in this case, cos 90 is become sin 0, which is equal to 0. So the perpendicular arms that does not contribute any magnetic field. So the magnetic field produced by the two perpendicular arms QR and SP becomes 0. So QR and SP becomes 0, 0 plus 0. But outside the region, the magnetic field is very weaker and that has become 0. Okay. So outside also the magnetic field becomes 0. So the total magnetic field that can be contributed by the one single arm, that is PQ in the rectangular loop, that is along the direction of the magnetic field. Therefore, close to integral PQRS into B vector dl, which is equal to B vector integral PQ dl, which is equal to BL. Okay, so that we can find it. But how many turns the solenoid have, we don't know. So the number of turns in the particular length in which the current entering through it. Okay, number of turns in the particular length of the solenoid in which the current is entering to it, that is equal to the total current enclosed by the loop. Therefore, using which rule we can use? Using Ampere's circuital law. Using the Ampere's circuital law, what does Ampere's circuital law says? The total magnetic field for any enclosed surface, which is equal to the total magnetic field for any enclosed surface, which is equal to mu naught times the total current enclosed, mu naught times the total current in the loop PQRS, in the loop PQRS. So mu naught times the total current in the PQRS, that is number of turns in the rectangle and the current. The total current, we can say number of turns in the rectangle, PQRS into current I, which is equal to mu naught into number of turns in the rectangular loop into the current entering to it. So already we have got this value, closed integral PQRS BDL, which is equal to BL. So instead of this we can substitute BL. So the length on the both sides is common. Therefore, the total magnetic field inside the solenoid will be mu naught times the turns in which the current entering to it. So this is the magnetic field, total magnetic field inside the solenoid. Okay, where mu naught is the permeability in free space. That value also we found already. That is equal to 4 pi into 10 to the power minus 7. So this is the magnetic field produced inside the solenoid. But at the end, outside near the end, the magnetic field will be half than inside. உள்ள இருக்கிறத விட அதோட எண்ட்ல பாத்தீங்கன்னா magnetic field எப்படி இருக்கும், அதுல பாதியா இருக்கும். So that is mu naught Ni by 2. And the outside the magnetic field will be mu naught Ni by 2. Okay, so I'll repeat once again. The same method only we are going to determine the magnetic field for the toroid. Okay, toroid we will see in the next class. Now the solenoid. Solenoid is nothing but a piece of equipment used to produce magnetic field. Mostly it is used in the motor and some electrical devices. For what? To produce a magnetic field. Okay, and this length of the solenoid is greater than the radius of each turn. Okay, on the soft iron frame they wind the copper wire, no? So, and each circular turns have a radius, but the radius is very small compared to the solenoid. For a long solenoid, the length is greater than the radius of each turn, but these copper wires are insulated, which was placed very closely. Suppose if the turns are more and more, then the magnetic field will be zero at their axis. Okay, so then only each copper coils are well insulated, which was placed very closely. Suppose it is very closely packed and it is too long solenoid, the magnetic field produced at the center alone, that is axial center alone, will be zero. But anyway, inside the magnetic field will be uniform, that is parallel field lines. But externally, it is a externally the field lines are closed lines. Okay, externally the field lines are curved lines. So in the solenoid, externally the field lines are curved lines that emerge from north and merge in the south, but inside the magnetic field lines are parallel. Okay, so that magnetic field only we are going to determine. Here they given the cross-sectional view of the solenoid. At one place in the upper end, the field is emerging out. Wire வெளியில வருது, மறுபடியும் உள்ள விட்டு இப்படியே நம்ம roll பண்ணிட்டே இருக்கோம். So we have a long turn. So at every point the current is emerging out. So the direction of the magnetic field will be anti-clockwise in the upper end field. Here the wire is going into the plane. So the current is going into the plane. So the field is produced in clockwise. So finally one place is the field line is emerging out of the plane and entering externally from north to south, internally from south to north. Now our aim is to determine the magnetic field inside the solenoid. So we have taken an imaginary Amperian loop. In this rectangular imaginary Amperian loop is PQRS. Here PQ is the arm which is along the direction of the magnetic field, but QR and SP is perpendicular to the direction of magnetic field. So there it won't produce any magnetic field. Moreover, RS is outside the solenoid. So the magnetic field also is zero. So the magnetic field produced only will be the arm which is along the direction of the magnetic field. So that alone we have considered. So that is equal to BL. Okay. Then because magnetic field is a constant, it's a uniform. So the line segment alone we integrated. Then we will get BL for a particular length of the solenoid. Now we are using Ampere's circuit law. According to Ampere's circuit law, for any closed surface, the total magnetic field is produced, that is equal to mu naught times the total current enclosed. So total current enclosed is nothing but, in this case, number of turns in the PQRS in the current entering to it. Number of turns. அப்ப இந்த லென்த்துக்கு எவ்வளவு டர்ன்ஸ் இருக்கு நமக்கு தெரியாது, அதுல எவ்வளவு கரண்ட் போகுது. So the total current enclosed is equal to NLI. On both sides the length is constant, so we can eliminate. Then finally we arrived the magnetic field inside the solenoid. This is uniform magnetic field, mu naught Ni, where mu naught is permeability in free space, N is the number of turns in the particular length, then I is the current entering through the solenoid. Okay, but note important point. Comparing inside, the magnetic field near the ends, near to the north pole or the south pole, that will be off than inside. So உள்ள இருக்கிறத விட வெளியில magnetic field எப்படி இருக்கும், பாதியா தான் இருக்கும். Okay, next we are going to discuss about the toroid. Same like a solenoid, toroid also a piece of instrument used to produce the magnetic field, but the shape is different. It is a ring shaped solenoid. ஒரு solenoid அப்படியே வளைச்சு நம்ம current pass பண்ணா, so the ring shaped solenoid is called toroid. About the toroid only we are going to discuss. Now we are going to discuss the magnetic field produced by toroid. The previous class we have discussed how to produce a magnetic field by a solenoid. A solenoid is nothing but a long insulated circular coil in the form of helix, and their length is much greater than the diameter of the each circular turns. Okay. Now if the solenoids are joined are bended in the form of a circle like a ring shape, this ring shaped solenoid is nothing but a toroid. Actually solenoid and toroid both also use as a instrument used to produce a magnetic field. So toroid. Actually the toroid is nothing but a hollow cylinder or a hollow circular ring on which a large number of insulated turns a large number of insulated turns of metallic wires are closely wound then it is called as a toroid. Actually a toroid is an actually பாக்க எப்படி இருக்கும்னா இமேஜின் பண்ணிக்கங்க circular ring மாதிரி so like a circular ring. So this is a toroid, it's like a donut, so on which a metal wire is wounded, which is very closely bonded. So or metal wire போயிட்டு into the toroid and then it is emerging out again into the toroid, இப்படியே bend பண்ணி சேர்த்திருப்பாங்க. இது வெளியில வந்துரும். So current is entering through the toroid, current is coming out through the toroid. So இப்போ நம்ம என்ன பண்ண போறோம்னா our aim is to determine the magnetic field of the toroid. So at the three different places, this is exact center of the toroid, but first point P is the point we are going to determine, and second point S, which is on the toroid, third one is outside the toroid, that is at Q. So now our aim is to determine the toroid at the three different points P, S, Q, whereas the magnetic field here is along the toroid. So நமக்கு magnetic field இங்க தான் maximum இருக்கும், on the surface centrally இருக்காது. So அதை எப்படி prove பண்ண போறோம்? Moreover, the magnetic field produced by the toroid is similar that of what? Solenoid. அப்ப solenoid magnetic field toroid ஓட magnetic field similar. So how it is? So we can say that a toroid is an endless solenoid in the form of ring. பார்க்க நமக்கு ring மாதிரி தான் இருக்கு, in the form of ring. So this is about the solenoid, toroid. So the toroid also used to produce the magnetic field. Okay. So here, so let how many turns we have, we don't know. So let n be the number of turns in the per unit length. அதாவது ஒரு 1 மீட்டருக்கு இல்ல 1 சென்டிமீட்டருக்கு எவ்வளவு டர்ன்ஸ் இருக்கு. So let n be the number of turns per length. So let n be the number of turns per unit length. I forgot to mention unit length, which means for 1 meter how much turns. Then I is the current entering through the toroid. I is the current which is entering through the toroid. Okay, and we are going to calculate the magnetic field of an ideal toroid. For an ideal toroid, the coils are closely wound. In the case of ideal toroid, the coils are closely wound. ரொம்ப நெருக்கமா சுத்தி வச்சிருப்பாங்க, closely wounded. Okay. Moreover, the constant magnetic field is set up inside the toroid in the form of concentric circular magnetic field lines. Okay. A constant magnetic field is set up inside the toroid in the form of concentric circular magnetic field lines, and this direction of the magnetic field is tangent to the magnetic field lines at that point. The direction of magnetic field, that is the direction of the magnetic field is tangent to the direction of the field lines, direction of magnetic field lines of forces. This is one important thing. And then now we are going to assume like this. In the toroid oda cross sectional view, adu apdi irukna cross sectional cut panna eppadi irukum. The cross sectional view of the toroid we are going to see now. So this is the actual toroid. Okay, this is the actual toroid. So we have the 3 points. Okay, this is exact center, but point P, S, Q. These are the 3 points we are considered. No, so we have the points P, S, and Q. P, S, and Q. இதை சுத்தி நம்ம ஒரு imaginary Amperian loop. Now we consider the Amperian loop 1. This is the first Amperian loop at a point P. Then the second Amperian loop is here. This is the second Amperian loop at S. This is the second Amperian loop, and the third Amperian, actually first Amperian loop is inside the toroid, second Amperian loop is on the toroid, that is on the surface of the toroid, third Amperian loop is outside the toroid. The third Amperian loop is outside the toroid. So this is the third Amperian loop which is outside the toroid. So P, S, and Q. This is the third Amperian loop. So here the first Amperian loop on P, second that is inside the toroid, second Amperian loop is on the surface of the toroid, third Amperian loop is outside. So 1 is inside, 3 is outside, the second loop is on the surface of the toroid. So we need to calculate the total magnetic field of this given toroid. So the cross sectional view, now we are going to draw the cross sectional view. In this cross sectional view, see here in the point enna idu emerging out of the plane. So all these cases is out of the plane. So the field is emerging out. So in all these cases the field is emerging out of the plane. But இங்க பாத்தீங்கன்னா into the plane. நீ பாருங்க இப்படி எடுத்தா இங்க உள்ள போயிட்டு வளைச்சு திருப்பி வெளிய எடுக்கறோம். அப்படியே பின்றோம். சுத்திட்டே போறோம். இது மேல கயிறு கட்ட மாதிரி. So அப்போ coil is entering into the plane, இங்க emerging out of the plane, again into the plane, is emerging out of the plane. So again into the plane and emerging out of the plane, இப்படியே போயிட்டே இருக்கும். Then into the plane, emerging out of the plane. So இப்படியே வளைஞ்சு வளைஞ்சு சுத்திட்டே போயிட்டு இருக்கு இது மேல, கரெக்ட்டா? So அப்ப இந்த இடத்துல எப்படி இருக்கும்? So here we have into the plane, it's a cross. So all these places we have a cross. Okay, that's it. So இப்போ பார்த்தோம்னா இப்போ நமக்கு first loop, first Amperian loop, அதோட சென்டர்ல இருந்து இருக்கிற ரேடியஸ் r1, second Amperian loop அந்த சென்டர் டொராய்டோட சென்ட்ரல் ஆக்சிஸ்ல இருந்து இருக்க ரேடியஸ் it is r2, and the third Amperian loop which is outside அதனோட ரேடியஸ் r3. Okay, so we'll take and write, let 1 2 3, let 1, 2, 3 are, what is the 1 2 3? Circular Amperian loop. Circular Amperian loop. Okay. Similarly, the corresponding radius r1, r2, r3 are, what is r1, r2, r3? Radii to be transversed in clockwise. இதெல்லாமே எப்படி இருக்கும்னா it's a clockwise. So all this in a clockwise. So radii to be transverse, to be traversed in clockwise. Okay, so இதில் இருக்க எல்லா radius R1 inner first loop, R2 is the second loop, radius of second loop, R3 is the radius of third loop, so that the P, S and Q lie on them, so that P, S and Q may lie on them. Okay, so now our aim is to determine the magnetic field of ideal toroid. So we are going to find the magnetic field of ideal toroid. So based on this diagram, now we are going to find the magnetic field of an ideal toroid. How to calculate the magnetic field of an ideal toroid? So this diagram is very important. So based on the diagram only, we are going to calculate the magnetic field. Okay, at first, listen, loop 2, 3. This is loop 2 and loop 3. So both, what happens? Loop 2 and 3 cut the toroid. Loop 2, 3 cut the toroid. Okay, each turn of current carrying wire, each turn of the current carrying wire each turn of the current carrying wire is cut once by loop 2 and twice by loop 3. What is the meaning? So நமக்கு இப்போ 2 and 3 மட்டும் எடுத்திருக்கோம். அப்போ 2 and 3 வந்து அதுதான் டொராய்டே கட் பண்ணுது, இமேஜினரி லூப். இதுல பாத்தீங்கன்னா each turn of the current carrying wire, இப்போ இந்த இதுக்குள்ள இருக்க டர்ன்ஸ்ல ஒவ்வொரு டர்னும் லூப் 2-வை ஒரு டைம் கட் பண்ணுது, பட் லூப் 3-யை 2 டைம்ஸ் கட் பண்ணுது. ஏன்னா இதுல இருந்து வந்து இது ஒரு தடவை போயிட்டு இங்க ரெண்டாவது தடவை வருது. அப்போ இப்படிதானே வருது. இது வந்து வெளியில் இருக்கிற லூப் 3, இது லூப் 2. இப்படி வரது இங்க ஸ்டார்ட் ஆகி 1 டைம்ஸ், லூப் 2 ஒரு டைம் கட் பண்ணிது, பட் மறுபடியும் லூப் 3 போகுது. அப்போ லூப் 3 பாத்தீங்கன்னா cut once by loop 2 and twice by loop 3. So now we are going to calculate the magnetic field at each point. So first, let B1 is the magnetic field along B1 is the magnetic field induction along loop 1. Therefore the line integral unna paathathai dhaan. So line integral B1 along loop 1 is closed integral, that is line integral 1 B1 dl, which is equal to closed integral L1 B1 dl into cos theta, but it is along, so 0. If this cos 0 degree is equal to 1, then we have B1 closed integral L1 under dl, so which is equal to B1 into 2 pi R1. Okay, here the loop 1 is encloses no current. Moreover, loop 1 is encloses no current. That is very important thing. Loop 1 is encloses no current. So now we are going to use Biot-Savart law. According to Biot-Savart law, how will you apply? So the closed integral L1 and B1 dl which is equal to mu naught times the current entering into the loop. So mu naught times current entering into the loop. But loop 1 in the loop kulla idukulla irukku ila current pass aguma? No. In the loop kulla current entry agala. Loop 2 3 la vena irukkalam. Adhulum pathina 2 la irukum but 3 la possible illa. Appo loop 1 kum loop 3 kum similar. This is 1, this is loop 2, this is loop 3. Okay, so loop 1 is not enclosed by any current. If loop 1 is not enclosed by any current, this value is 0. Therefore, the total current enclosed by the loop 1 will be 0, which is equal to mu naught into 0. Because loop 1 encloses no current, so the total magnetic field will be 0. That is B1 into 2 pi R1 is equal to 0. This procedure is same for loop 3, because loop 3 also not encloses any current. It is same for loop 3, which is outside the toroid. That also not encloses any current. Not encloses any current. Okay, the same derivations only you are going to use for magnetic field at the third loop, which is outside the toroid. But now we want to determine the magnetic field on the surface of the toroid. So on the surface of toroid, the same process. So let B, on the surface the magnetic field is B, as I mentioned already, it is along. So B is the magnetic field, induction along the loop 2. Okay, magnetic field. So the line integral, what will be the line integral? So line integral B along the loop 2 is closed integral loop 2 into B dl, which is equal to closed integral loop 2 B dl. What is the value? Is cos theta. Yes, it is cos 0 degree. Therefore, we have B into closed integral loop 2 into dl. So what will have? This value is equal to B into 2 pi R2. Okay. Now we use Biot-Savart law. According to Biot-Savart law, you are applying in the above cases. What is the Biot-Savart law? For any closed surface, the magnetic field on the any closed surface, which is equal to mu naught times the current enclosed. Mu naught times the current enclosed. So what mu naught times current enclosed, that is the total current enclosed by the surface, which is equal to mu naught into, what is the current? Total current enclosed. Yes, total current enclosed will be 2 pi R2 into Ni. Already this value we found, this closed integral value, which is equal to B into 2 pi R2, which is equal to mu naught into 2 pi R2 Ni. And n number of turns irukula, adula evlo turns irukku namakku theriyadhu. So we have n number of turns in this toroid. So 2 pi R2 and 2 pi R2 cancel. Finally, we have the magnetic field on the surface, which is equal to mu naught Ni. So இத பாத்தீங்கன்னா நமக்கு solenoid என்ன magnetic field கிடைச்சதோ அதேதான் toroid. So it is similar to solenoid field. Therefore, solenoid and toroid both also produce the same amount of magnetic field. But according to the situations, it may be designed whether in the form of a long circular solenoid or a circular ring. Okay, circular ring in the toroid, long cylinder in the like a cylindrical coil in the solenoid. But solenoid magnetic field is similar to toroid. I will repeat once again, listen it carefully. solenoid and toroid both also used to generate magnetic field. Okay, எப்படி இருக்கும்னா how it was designed na a hollow circular ring on which a large number of turns of metallic wires are closely wounded. Like a copper coil வந்து ரொம்ப closed n number எவ்வளவு turns இருக்குன்னு நமக்கு தெரியாது. Let n be the number of turns per unit length. அதாவது ஒரு மீட்டருக்கு எவ்வளவு turns இருக்கும். சோ அப்ப நம்ம எவ்வளவு பெரிய ஷேப் எடுத்துக்கோமோ அப்ப அதனோட 1 meter length க்கு எவ்வளவு turns. It may be 1000 turns or 10,000 turns. Okay, in a mixer grinder like motor, many devices they'll use this toroid only. Okay, so the large number of insulated metallic wires which was placed very closely. So as toroid is an endless solenoid in the form of ring. So ring shaped toroid, ring shaped solenoid தான் நம்ம என்னன்னு சொல்றோம், toroid அப்படினு சொல்றோம். இப்போ இதனோட cross sectional view அது பார்க்கிறதுக்கு முன்னாடி இங்க பாத்தீங்கன்னா wire வந்து உள்ள in, இது out. So இங்க wire in, இங்க out, which means field is entering into the plane, இங்க field is emerging out. மறுபடியும் field is emerging in, field is emerging out. இப்படியே தான் wind பண்ணிருப்பாங்க. windோட past tense wound-ஆ. So இப்படியே தான் மேல சுத்தி வச்சிருப்பாங்க. Closely they wound it. Okay, so now we are going to calculate the magnetic field at the 3 points. Let P be the first point which is at the center of the toroid, and S be the second point which is at the surface of the toroid, and Q be the point which is outside the toroid. So in the point பொறுத்து நம்ம ஒரு imaginary line draw பண்றோம். This is an imaginary Amperian loop. So first center la first loop 1 at point P having the radius R1, loop 2 having the Amperian loop radius is R2, yes, and loop 3 which is outside, that is in anti-clockwise direction, clockwise directions. All this in a clockwise direction only. So all this is a clockwise direction only. So R1, R2, R3 are the radius of the loop 1, loop 2 and loop 3. Okay, this is out of the plane, this is inside the plane. அதான் மென்ஷன் பண்ணிருக்கேன். இப்போ நம்ம என்ன பண்ண போறோம், ஒவ்வொரு லூப்புக்கு நம்ம ஃபீல்ட் கால்குலேட் பண்ண போறோம். ஃபர்ஸ்ட் பார்த்தோம்னா நமக்கு லூப் 2 and 3 கட் தி டொராய்ட். ஏன்னா இந்த டொராய்டை கட் பண்றது லூப் 2 and 3 மட்டும் தான் கட் பண்ணுது. அதுல yes, loop 2 that cut the toroid once, but loop 3 cut the toroid twice. Okay, in the second loop இருக்கு இல்லீங்களா, second loop that cut the toroid once, and third loop that cut the toroid twice. முக்கியமான point. And then let B1 be the magnetic field inductions along L1. B1 is the first magnetic field inductions along L1. Okay, first loop. So the line integral of the B1 along L1 is given by, as usual, அதோட radius நமக்கு தெரியும், அதை வச்சு போட்டாச்சு R1. ஏன்னா first loop ஓட radius R1. Okay, ஏற்கனவே எழுதிருக்கேன், R1, R2, R3 be the radius of the loop 1, loop 2 and loop 3. So we found their magnetic field. This we are going to substitute in the Biot-Savart law. What the Biot-Savart law says? For any closed surface, the magnetic field induction produced, total magnetic field induction produced, which is equal to mu naught times the total current enclosed by the loop. So the mu naught times the total current enclosed by the loop. Actually, இதுக்குள்ள current போதா? No current is enclosed by the loop 1. So அப்போ current value is 0, then entire value is 0. அப்போ நமக்கு first loopல magnetic field is 0. அடுத்து எங்க பார்க்க போறோம்னா இதே தான் third loop which is outside. So it is same for loop 3 which is outside, so vanishes 0. அப்ப third loopலயும் magnetic field 0. அப்ப magnetic field எங்க மட்டும் தான் இருக்கும்? It is maximum on the surface. அத தான் நம்ம கால்குலேட் பண்ண போறோம். So let B be the magnetic field inductions along the loop 2. So the line integral of the magnetic field that is loop 2 which is equal to in the same way. So அத அப்படியே Biot-Savart law substitute பண்ணுங்க. So after substituting the Biot-Savart law, for any closed surface, the total magnetic field inductions which is equal to mu naught times the current enclosed by eta. So mu naught times the total current enclosed. Total current எதுக்கு equal? On the second surface, second loop on the surface. So அதனோட circumference 2 pi r, அது எவ்வளவு turns இருக்கு நமக்கு தெரியாது, then current entering into it. So இத வச்சு மல்டிப்ளை பண்ணா 2 pi r2 on both sides we can cancel. Then finally the magnetic field on the surface of the toroid which is equal to mu naught Ni. So this is similar for solenoid magnetic field. அப்ப solenoid க்கும் toroid க்கும் we have a same magnetic field, but this is for an ideal solenoid. Okay, this is a magnetic field for ideal solenoid, but நமக்கு பேசிக்கா practically solenoid, this is for ideal toroid, but practically in the case of toroid, some little magnetic field will be present on the outside, not much more, கொஞ்சமா இருக்கும். Okay, practically there is a small amount of magnetic field which is outside the toroid, and the magnetic field is similar. The toroid magnetic field is similar to that of solenoid. Okay, toroid and solenoid both have same magnetic field. Thank you.